relativity, momentum is mass times proper velocity. There are two velocities to choose from: ordinary velocity v, dx by dt, and proper velocity u, dx by d tau. Classical physics gives you no clue which one you should use in the definition of momentum, but the internal structure of relativity suggests that mu is a good definition and mv would be a lousy definition. Anyhow, fact is, this is the definition of momentum in relativity. You can define something any way you want to, of course. The issue is whether it's then used physically, and we'll come later on to see why this definition of momentum is useful. Gamma, of course, is the ubiquitous factor 1 over root 1 minus v squared over c squared. And for today, I'm not going to talk about proper velocity at all, so I'll write all formulas in terms of ordinary velocity. Well, in addition to the relativistic momentum formula, Einstein also introduced relativistic energy. E is equal to gamma mc squared. This formula, frankly, is a little bit harder for me to motivate at this level. I know of two elegant and sophisticated ways of getting your hands on the formula for relativistic energy, but no particularly clean one at quite this level. I may show you, if there's time today, I'll show you one way of obtaining that formula, motivating that formula via the work energy theorem. But I want to play with it, work with the relativistic energy formula today. That's my main purpose, and we'll come back to where it came from. mc squared over root 1 minus v squared over c squared. By the way, if you're used to the idea from the newspapers or whatever that Einstein said energy is mc squared, this is not true. He said energy is gamma mc squared, but I guess the newspaper don't like to print the gamma, so they just call it mc squared. But relativistic energy is gamma mc squared. A couple of comments on that energy formula. First of all, even if the particle is at rest, it still has some energy according to this formula. Because if the particle is at rest, then v would be 0, the denominator becomes 1, and I just get mc squared. I get what we call rest energy. That's, if you like, the sort of residual energy that's stored in a particle even if it's not moving at all. R, I'll use the letter R for that, although it's not terribly standard. R is equal to mc squared. There's the mc squared without the gamma, because the gamma is 1 if you're at rest. That's rest energy. Residual energy that's there, according to Einstein, even for a particle at rest. If it's moving, then it has some extra energy in addition to that rest energy, which we call that extra energy, energy associated with the motion of the particle. That's the generalization of kinetic energy, right? That would be the energy that's attributable to the motion itself. So kinetic energy due to the motion is not this total energy, Einstein's total energy E, is that minus the amount that the thing would have had even if it had been at rest. So kinetic energy, T, is equal to E, the total energy, minus R, the rest energy. Which is to say, it's gamma mc squared minus mc squared itself. Or if you like, gamma minus 1 mc squared. So there's the energy associated with the motion of the particle, the kinetic energy in special relativity. That's the quantity that ought to reduce to 1/2 mv squared if you're going at low velocities to the ordinary classical formula. But the derivation is cute, but it's not trivial. How t reduces to 1/2 mv squared for non-relativistic speeds. By the way, what would I mean by a non-relativistic speed, technically? Something where relativity is not going to be relevant anymore. That means v much less than c, right? If you get velocity up close to c, then it's going to be relativistic. But I'm talking about v much less than c. In that, the classical realm, the old classical formulas should apply. They do for momentum, by the way. If v is much less than c, then this denominator is essentially 1, and I just get mv. So how does t reduce to 1/2 mv squared for non-relativistic speeds? I have to figure out how to write gamma approximately for v much less than c. I'm not sure whether you will have seen this kind of argument or not, but gamma is equal to 1 over the square root 1 minus v squared over c squared. That's equal to 1 minus v squared over c squared to the minus 1/2 power, if you like. Do you know how to approximate? And the v squared over c squared is by assumption very small. We're in the non-relativistic domain. So this is of the form 1 plus epsilon, where epsilon is a very small number, very small to, compared to 1, raised to the power n. In this particular instance, the epsilon is minus v squared over c squared, and the n is minus 1/2. But do you know how to do this in general? How to approximate 1 plus epsilon to the n? This may be something you know, and it may well not be. I don't know. What you use is the binomial theorem. Remember binomial theorem? Oh man, ages ago. Well, the first two terms in the binomial theorem says 1 plus epsilon to the n is 1 plus n epsilon, and then there's some other terms, plus n times n minus 1 over 2 epsilon squared, and so on. But I'm only interested in the first two terms. I claim that 1 plus epsilon to the nth power is approximately equal to just plain 1 plus n epsilon. How does this work? Let's check it. For small epsilon. Well, what would be a good power to try? Let's make it easy. N equals 1. What would I get? 1 plus epsilon raised to the 1th power is just 1 plus epsilon. Is that 1 plus n epsilon? Sure it is. It's 1 plus 1 times epsilon. Yeah, in that case, it's actually not an approximation, it's exact. How about 1 n equals 2? 1 plus epsilon squared. What would that be? If I squared that out, it's 1 plus 2 epsilon plus epsilon squared. Here is the 1 plus n epsilon, but there's some extra junk. However, the extra junk is very small by assumption, because I say epsilon is small. If epsilon is small, then epsilon squared is very small. Isn't that right? For example, suppose that epsilon was equal to 0.01, then epsilon squared would be 0.0001. Very small. So I throw away the epsilon squared term, and I get approximately 1 plus 2 epsilon, which is exactly what I claim, 1 plus n epsilon. But if you did it for n equals 3, you know how to cube a binomial? You can multiply it out. Multiply out 1 plus epsilon times 1 plus epsilon squared, if you like. It's 1 plus 3 epsilon plus 3 epsilon squared plus epsilon cubed. Is that approximately 1 plus 3 epsilon? Yes, it is, because that would involve keeping just the first two terms, throwing away epsilon squared on the ground that is tiny, and epsilon cubed on the ground that is even smaller. So you see what the name of the game is? Here, it works for positive powers, but the beauty of it is that it works for negative powers as well. N equals minus 1, then what would I have? 1 plus epsilon to the minus 1. You happen to know what that is as an expansion? I don't know if you've seen this or not. It's the harmonic series or the something or other series. It's 1 minus epsilon plus epsilon squared minus epsilon cubed, and so on, which is again approximately 1 minus epsilon this time, 1 plus n, but n is minus 1 times epsilon, and I throw away all the other terms on the ground which are very small. But how about n equals 1/2, for example? 1 plus epsilon to the 1/2. I don't know how this goes, but it's going to be 1 plus 1/2 epsilon. I'll tell you that's going to be true if epsilon is quite small. For example, you could use this for very fast mental arithmetic. If you had a quantity like somebody says to you, what is the square root of 1.0002? You could do that in your head, because this is the square root of 1 plus 0.0002, which by that binomial theorem is approximately 1 plus 1/2, the factor there, 0.0002, which is 1 plus 0.0001, which is 1.0001. If you doubt me, check it out on your computer. Punch in calculator. Punch in 1.0002, and you will get 1.0001, 0.0000, and then some other junk way down at the far end of the scale. But basically, it's 1.0001. See how it goes? Now, what we want in this case is n equals minus 1/2. That's what I want to approximate gamma. That would be 1 plus epsilon to the minus 1/2 is equal to 1 minus 1/2 epsilon. Again, you can check that out on your calculator. Try calculating the square root, 1 over the square root of 0.98, for example. You could do it in your head. It's 0.99. So, all of that is just to try to sort of motivate the formula that I propose to use to approximate gamma. Gamma is 1 minus b squared over c squared to the minus 1/2, which would be approximately, for small b over c, 1 minus 1/2, there's the n, times minus b squared over c squared, there's the epsilon, and then there would be higher order terms, but they're small, provided that b itself is much smaller than c. So this is equal to 1 plus b squared over 2c squared. How about that? If the velocity is rather small, then gamma is approximately 1 plus b squared over 2c squared. Did that make any sense to you at all? Is this a clear argument? Of course, you want to go to your math course to find out the absolute proof of the expansion here. I'm just sort of motivating it by giving you some examples so to build the answer and then telling you that it's true in general. It's actually fun to check these things on your calculator. There's nothing special about the 1/2. You could calculate the 1/19th power if you want of 1.0002 also, essentially in your head. So where are we? Gamma is approximately 1 plus b squared over c squared. Now what I was looking for is t. What is t? The kinetic energy approximately. Well, it's exactly equal to gamma minus 1. But gamma is approximately 1 plus 1/2 v squared over c squared. There's the gamma, and now I'm supposed to subtract 1 from that and multiply the whole works by mc squared. What do I get? The 1's conveniently cancel, and I get 1/2 v squared over c squared times mc squared. Whoa, the c squared cancel, and I'm left with 1/2 mv squared. How about that? The classical formula. So for very small velocities, small compared to the speed of light, in other words, the ordinary everyday realm, the kinetic energy that's given by Einstein's formula reduces to the kinetic energy that was given by Newton, half mv squared. As of course it should, because that's the everyday world we live in, and we know that physics works with the classical laws in that regime. So, end of a sort of awkward argument, but I just wanted to check that the kinetic energy that we obtain, total relativistic energy minus the rest energy, that reduces to 1/2 mv squared as long as the velocities are very small compared to the speed of light. Now, what can we do with relativistic energy? As I said before, you can define energy and momentum any way you please. The question is, are the definitions you came up with of any use in physics? So what is the physical use of relativistic energy and relativistic momentum? Answer, they are conserved. At least that's a big part of the answer. They have other uses as well, but basically they're conserved quantities. In fact, no hanky-panky here in contrast to the classical case. Relativistic energy and relativistic momentum are always conserved in all collision processes. These are the definitions. And now the physics. I mean collisions in a generalized sense before, that, two things that come together and stick together, that's a collision. One thing plus a part of the six is also a collision in a generic sense. Energy and momentum are conserved in all collisions. Classically, momentum is always conserved in collisions. Energy might or might not be. When you hit a collision problem, you've always got this nightmare. You need to study the fine print and find out whether they're secretly telling you that it was elastic or not. If it's elastic, then kinetic energy is also conserved. In the relativistic case, it is in this sense a lot cleaner. Energy and momentum are always conserved. Example. Suppose I had a lump of clay, 3 kilograms. And it's going at 4/5 the speed of light. Don't ask me how I got it going that fast. And it collides head-on with an identical lump going the opposite direction at the same speed. So here's the scene beforehand. The mass is 3 kilograms. It's going at 4/5 the speed of light, and it encounters another lump of clay going the other direction, 4/5 c, and its mass is likewise 3 kilograms. So here's the scene before. And the scene after. Those two lumps of clay stick together. Lumps of clay tend to, forming a single composite lump. How fast is it moving? Not moving at all, right? Is that clear? These two came in together symmetrically. The final lump, when it's all stuck together, can't be moving. Could you actually justify that with the law of physics? I mean, it's pretty obvious that the final lump is not moving, but what's the law of physics behind that? It's actually conservation of momentum, isn't it, right? If I had momentum for this one, I could calculate what it is if I was interested, but momentum for this one, whatever that is, this one is equal and opposite. So the initial momentum was 0, initial total energy momentum was 0, so the final momentum had better be 0 too. So here's the scene after, and it's at rest. So that's the collision I'm interested in. Let's see, 3 kilogram lump of clay going 4/5 c, collides head on identical lump, that is to say, mass also 3 kilograms going the other way. I'm writing out the conditions here in gory detail because this is an absolutely critical example. Collides head-on with a identical lump going in the opposite direction at the same speed. Question: what is the mass of the final composite lump? Call it capital M. If you think the answer is 6, not a bad guess, but you're in for a big surprise. Because energy and momentum are conserved in relativity, but you'll notice I did not say that mass is conserved in relativity. Indeed, mass is not conserved in relativity, and none of elementary particle physics, the basis for everything we do, none of elementary particle physics would be possible, actually, if mass were conserved in relativity. Mass is simply not conserved. I'm getting ahead of the game. That's the punchline. I shouldn't tell it to you until it's hit you over the head in an actual calculation. But I'd let the cat out of the bag. Mass is not conserved in relativity. Okay, let's see how it goes. Momentum conservation in this problem is trivial. 0 equals 0. What do I have to work with? Conservation of energy. So I want to add up the energies of those two particles before the collision, set them equal to the energy of this particle after the collision. Got the picture? So what is the energy before the collision? Well, gee, I need to know what the gamma factor is. So gamma for something that's going at 4/5 speed, 4/5 speed, you happen to know what the answer is? This is one of those nice ones, that's why I chose 4/5. Gamma is 1 over the square root of B over C. The C's will cancel. It's just going to be 4/5 squared. 1 minus 4 over 5 squared, which is 1 over the square root of 1 minus 16 over 25, which is, if I multiply top and bottom by 5, bring the 5 inside the square root, is 25 minus 16, then 25's cancel in the second term. That's 5 over root 9. But root 9 is 3, so it's 5/3. That's the gamma factor for each one of those. 4/5 is nice. 3/5 is also nice. 3/5, the gamma would be 5/4. So anyhow, that's the gamma factor. So what's the energy of one of them? This one here, for example. According to Einstein, it's gamma mc squared, so that's 5/3 times m, but that's 3. No wonder he chose 3. Okay, 5/3 times 3 times c squared. The 3's cancel, and I get 5c squared. That looks funny, but of course there's kilograms buried in the 5. Okay, so that's the energy of this one alone. What's the energy of this one? 5c squared. Very good. So what's the total energy if I added the two together? 5 plus 5, 10c squared. The initial energy is 10c squared. Everybody with me? Okay, that's got to be equal to the energy of this final composite lump. What is that? Easy. The final composite lump isn't moving anywhere. We checked that at the very beginning. So this thing is at rest. The only energy it's got is rest energy. Rest energy, mc squared. So this is equal to capital M c squared, the final energy, all the rest energy. The c squareds cancel, and I conclude m equals 10. 10 what? 10 kilograms, of course, if I think we're using units all the way through. So the final mass is 10 kilograms. Those of you who thought it was going to come out 6 kilograms, It's not. It's 10 kilograms. Mass was actually produced in this reaction. Where did it come from? Actually, let's talk about the reverse process, because this is a little bit hard to set up in a laboratory that you literally would smash two lumps of clay together. But the reverse process, where a single lump busts apart into two or more pieces that go flying off, that happens all the time. Any disintegrating elementary particle is exactly an example of that. The particle sitting here busts apart. In that case, the mass of the final product is less than the mass of the original one. The newspapers say that mass was converted into energy. That's supposed to sound really deep. Have you ever read that? You must have. That according to Einstein, mass can be converted into energy. Any student of physics should howl when they say mass can be converted into energy. Mass and energy don't even have the same units. This is an absolutely ludicrous statement. It's not just that there's an engineering problem or something for converting mass into energy. Mass can't be converted into energy for purely logical reasons any more than you could convert feet into antelopes or something like that. They're just different things. You can't convert mass into it. What did happen here? What did happen when a heavy object busts apart into two light ones that fly off at high energy? What happened was that rest energy was converted into kinetic energy. That you can do, a simply conversion of one form of energy into another kind. But I don't suppose you sell newspapers by saying in the atomic bomb, rest energy was converted into kinetic energy. Sounds much nicer if you say, more impressive if you say mass was converted into energy. It irritates me. In this problem, kinetic energy, these two had a lot of it, was converted into rest energy. This one has more rest energy, more mass, mc squared. So this has more mass, less kinetic energy. This has more kinetic energy, therefore less rest energy, less mass. So you can convert rest energy into kinetic energy, or vice versa, no problem. But don't tell people you convert mass into energy, that's just stupid. I'll give you an example. I said a moment ago that none of elementary particle physics, nothing would happen in elementary particle physics if there were a law of conservation of mass in relativity. Here's an example. The neutron decays. I don't know if you know what the products of the neutron decay are, but the neutron spontaneously decays. A free neutron outside of atomic nucleus. If one's sitting on the table would decay after about 10 minutes. It produces a proton, an electron, and a neutrino. But I tell you, if you add up the mass of the proton, the mass of the electron, and the mass of the neutrino, add them all up, you come out with something that's a little bit smaller than the mass of the neutron. Some rest energy in the form of a higher mass of the neutron is converted into kinetic energy of the decay products as they fly off at high speed. So this is a case of rest energy converted into kinetic energy, or if you're writing a newspaper story, mass converted into energy. That happens to be a delicate case because the proton, electron, and neutrino weigh almost as much as the neutron, but just a hair less. There are other extreme examples where huge amounts of mass disappear in the process, producing huge amounts of kinetic energy. Maybe I'll give you the extreme example in a moment, but I have to set up a couple of pieces of machinery first. Yeah.
In the example, the 4 kilograms we pick up, what exactly like is that 4 kilograms in the form of? Is like 4 kilograms of clay spontaneously cut up, or is it in some other form?
Very good question. Let me twist your question around a little bit. Is this guy telling me that there are more atoms in the final one than there were here? No, I'm not saying that. Actually, the number of atoms here is exactly the number of atoms that was here, plus the number of atoms that were here. Well, what's different about those atoms here? Classically, what would we say? Classically, kinetic energy has disappeared in this collision also. But classically, how do we account for that? We would not, classically, we wouldn't have said the rest energy increases. We didn't know anything about rest energy. But looking at this same process at low speed, you'd say two lumps of clay collided. They produced a final lump. The kinetic energy had obviously disappeared. Where did it go? What would you say classically?
Like in heat.
Heat, exactly. What is heat? That means that all of the atoms and molecules in this thing are moving around faster than they were before. What relativity tells us is that a hot potato or a hot lump of clay actually weighs more than a cold lump of clay. In a certain sense, the mass of this composite lump is a measure of all of the energy that's in that thing, including actually kinetic energy of the individual molecules that are going on there. This is actually a measure of total energy of the whole thing. So, if we were telling this story classically, we would say kinetic energy disappeared and the final lump was hotter. Relativity says that that hotter lump actually weighs more. It's more massive, and I can take account of the equation here by saying that the mass simply decreased by the amount that we would have called heat in the classical case. Yeah?
But if the increase of mass comes from kinetic energy, then why can't you say that the lumps of clay originally weighed 5 kilograms? Because they had the kinetic energy that later became kinetic energy in the form of heat.
It's energy with respect to the center of mass. Yes.
Okay.
I thought you were going to nail me for a different reason. I thought you were going to raise again the ugly head of relativistic mass, because, you know, if this were a more elementary course in which I was using Einstein's old notion of relativistic mass, I would say what's happened is that there are just as many atoms in here, but they're moving faster. And therefore, their relativistic mass is larger. Remember what relativistic mass was? This thing, gamma times the ordinary mass. So if you use the language of relativistic mass, you would say what's happening here is that these two lumps of clay smash together. This lump is hotter, therefore each atom in it is moving faster. Therefore, each atom has a larger relativistic mass, and all I'm doing is adding up the relativistic masses of all the pieces here. So this is one of several cases where the language of relativistic mass actually, in a certain sense, makes the argument a little bit cleaner.
In a way, Ben, it's exactly right. If you view the top system from far away, the difference is just the way the kinetic energy is distributed. In the top picture versus the bottom picture. Instead of all of the particles having their kinetic energy from extra motion in this direction, the one on the right and the left, it becomes randomized. But seen from far away, the system above does weigh exactly the same.
Let me put your argument a little bit different, if I may. Suppose that we stuck a huge black box around this whole thing.
Exactly.
With those things flying to each other, I'll put the thing on a bathroom scale. How much would it weigh? It would weigh 10 kilograms. That's what its mass would be. Looking inside, we know that actually some of that is in the form of kinetic energy, actually, and some of it is in the form of rest energy. And in the way I was telling the story here, I was talking only about the rest energy portion of it. But the bathroom scale actually weighs the total energy divided by c squared of whatever is in the box. So
In fact,
point is well
it's
taken.
one of the rare points that Feynman gets wrong, even though Feynman's lectures. He adds mass energy, rest mass energy as a separate form of energy in his list in that parable of Dennis the Menace. And it's not a separate form. Viewed from the outside, energy is mass. If you put
Yes,
a black
or
box
putting it in a black box,
the
yes.
total energy is the mass times these
Great.
vice versa.
Okay, I want to show you now two further implications of relativistic energy. One of them is just a useful formula relating energy and momentum. I shouldn't have erased the formulas for energy and momentum. Remember, E is equal to gamma mc squared, and P is equal to gamma mv. And gamma, of course, is 1 over root 1 minus p squared over c squared. What if I calculated the following quantity? E squared minus p squared c squared. I can't motivate this. I'm just going to try calculating that. Take it from me, it's going to produce something interesting. E squared would be gamma squared m squared c to the fourth. P squared would be gamma squared m squared v squared. And now I multiply that by c squared. Doesn't look too nice. Well, let me factor out gamma squared, that's a common factor, m squared, common factor, and c to the fourth. Then I would have just 1 in the first term, and in the second term I factored out c to the fourth, so that means it would be minus v squared over c squared, isn't that right? Because I took out 4 factors and there were only 2 there, so I had to put a c squared in the denominator. See anything suspicious here? 1 minus v squared over c squared. The thing in parentheses, what is that?
1 over gamma squared.
Very good. I was afraid somebody was going to say it's gamma squared. Actually, it's not. 1 over gamma squared, right? 1 over gamma squared would be 1 minus v squared over c squared. So this is 1 over gamma squared. How nice. There's a gamma squared out in front. Those two cancel, and the answer is just m squared c to the fourth. Let me rewrite this and put a box around it. My conclusion is e squared minus p squared c squared is equal to m squared c to the fourth. A nifty formula relating energy and momentum. In practice, it's more than nifty. Let me tell you a fact. Doing relativistic kinematics, conservation of energy and momentum, is in principle utterly easy. Easier than the classical case. Energy is conserved, momentum is conserved. Atom up before, atom up afterward. But I have to say, you could spend an afternoon getting tangled up in complicated arithmetic. I don't understand why it is, but even though the laws are utterly simple, somehow or other dealing with the factors of gamma and whatnot can tangle you up in nasty arithmetic. There is a wonderful trick for avoiding lots of it, and that is to remember this formula here. Why? Because this enables you to calculate E if you happen to know P, or P if you happen to know E directly, without you ever having to figure out what V is. Suppose you knew P, and you wanted to know E. Naively, you would say, well, here's the formula for P. I solve for V, but there's a V here, and there's another V in the denominator, and the square root in the gamma. Okay, I do some nasty algebra, and finally I extract V from it. Once I've got V, I have to calculate what gamma is. I stuff that back into this formula here. That's taken me 25 minutes, even if I didn't make any mistakes. But if I use this formula down here, I can go directly from P to E without ever calculating V. And I don't know why it is, but any time in relativity that you can avoid calculating V, do it. Calculating V is just, it turns out, a prescription for nasty algebra. So, the virtue of this is that it lets you get back and forth from E to P without calculating V. Very well. You'll see an example on the owl tonight. Now, one last item connected with relativistic energy. I would say it was a curiosity, except it turns out to be very important in practice. Massless particles. By that I mean m equals 0. It is massless. Massless sounds like it doesn't have any such thing as mass. By massless particles, we mean in physics a particle whose mass is perfectly okay, just happens to be 0. Classically, there's no such thing as a massless particle. How come? Suppose that you try to make a massless particle. Well, what is momentum P? P equals mv, classically, that would be 0, so it can't carry any momentum. What would its kinetic energy be? 1/2 mv squared. If m is 0, it's got no kinetic energy. Well, let's apply a force to it. Nope. F equals ma. If m is 0, F is 0. You can't apply a force to it. Well, maybe it can apply a force to you. No, by Newton's third law, the force it exerts on you is equal and opposite of the force you exert on it. This is a cipher, folks. It's got no energy, it's got no momentum, you can't touch it, it can't touch you, it's nothing. I've sometimes wondered if in classical domain, I mean, maybe you could have massless particles, but they just are totally out of communication with us. Well, okay, then they got nothing to do with physics, and I'm not interested in them from the point of view of a physicist. But I guess logically it's possible that there are massless particles, even in classical physics, but they just don't talk to us at all. Weird. But in relativity, you might think that the same argument would apply. What's the momentum of a massless particle? P equals mv over root 1 minus v squared over c squared. Well, you stick m equals 0, aren't you going to get 0? Energy, mc squared over root 1 minus v squared over c squared. Stick in m equals 0, aren't you going to get 0? Well, it looks like it because of the numerator, but closer inspection reveals a loophole for the congressman. You see it? M could be 0. And yet, the energy of momentum might be non-zero, provided that the denominator is also 0. If the denominator is 0 and the numerator is 0, then I get 0 over 0, and mathematicians tell me not to touch it. It could be anything. M could be 0, yet P and E non-zero. You could have a massless particle with energy and momentum, provided that the denominator is 0. When would that happen? V equals c, provided that it always goes at the speed of light. Curious, by the way, this formula over here, the one relating energy and momentum, has no such defect in it. I could put in m equals 0 then, and get a perfectly sensible result. Namely, e squared minus p squared c squared is equal to 0. If I put in m equals 0, which tells me, if I solve for E, this just says that E is equal to momentum times c, the magnitude of the momentum times c. what's the conclusion? In relativity, we can just barely conceive that there might be massless particles, m equals 0, provided that the velocity is c, they always travel at the speed of light, and E is equal to P times C. So those are the three conditions for massless particles. Personally, I would regard this whole argument as a joke. I would dream of telling it in public, were it not for the fact that there are in nature massless particles. They do always travel at the speed of light, and their energy and momentum are related by the formula E equals P times C. We are forced, therefore, whether we like it or not, to take this weird loophole seriously. This formula doesn't tell you what the momentum is. It tells you 0 over 0 for massless particles, and I don't know what to do with that. It's ill-defined. This formula doesn't tell you what the energy is. It's 0 over 0. That doesn't tell me what the energy is. It doesn't say that the energy is necessarily 0, mind you. It just tells me, I don't know from this formula what the energy is. I do have one connecting formula between E and P that survives, namely E equals P times C. There are such particles. They do travel at c. Do you happen to know the name of the most familiar example? Most common example of a massless particle that travels at the speed of light? The photon. That's the quantum of light itself. Of course it travels at the speed of light. Until 2 or 3 years ago, I would have put onto that list also all of the neutrinos. There are 6 different species of neutrinos, and they were thought to be massless. And now most people believe that they probably have a tiny but non-zero mass. But the photon certainly has 0 mass, or else lots of physics is in major trouble. Ask you a question. What's the difference between a really energetic photon and a not so energetic photon? Say, well, the really energetic photon's got more mass. No, they both got mass 0. Well, you say maybe a really energetic photon is traveling faster. No, they're both going at the speed of light. So what on earth is the difference between an energetic photon, a photon with a lot of energy, and a photon with not so much energy? Relativity has no answer to that question. It's not speed, it's not mass, because those are fixed, the same for both of them. Curiously, quantum mechanics does provide the answer to that question. A more energetic photon is bluer. Its color is different. A red photon of red light, is not very much energy. A blue photon of blue light, is a high energy photon. Nothing to do with relativity, has to do with the frequency, which comes in the quantum mechanical theory.